Okay, so for 307, this first video, I want to explain why you see that crazy dy dx thing and other dy's or dt's and dr's and lots of different symbols in this lesson. And it will help you when you get to 405 big time. So I like to just pretend that you're my student at the very beginning. You're just now learning derivatives. So pretend to erase everything you've known about the derivative except for that it's the slope of a tangent line and that crazy limit definition that you learned in chapter 2. Okay, so think back to algebra 1. You were given two words, well, four words technically, dependent variable, independent variable. And you were told what they meant a long time ago, but you've probably never used them since. Well, it's actually really important now because when we're talking about two variable system here, the independent variable is always the x-axis and the dependent is the y-axis. And one depends on the other. So for example, let me give you a real life example of why this matters. This is a picture of a website. It's where you can get the ocean tides and like current information. So I live near Fort Myers Beach. This was whenever I took a screenshot of this um, on this date actually. So hopefully it's not too old now. This is what the tides look like that day. So this represents, a periodic function, and they make predictions. The blue line is what they predict to happen, and the red line is what is actually happening. So like at a certain time, it tells you live what the water level is. So think about independent and dependent variable. It would depend on what time it is to tell you how high the water is, not vice versa, where the time does not depend on the height of the water. The height of the water depends on the time. So notice that the time is the bottom here, which is the x-axis, and feet above sea level here is the y-axis. So independent is always x, dependent is always y. And x is usually time. In real life, usually represents time. So anytime you're dealing with time, always the independent variable, unless it's otherwise stated elsewhere, and it would be in that case. Okay, so let's consider x to the second power. Y equals x to the second power, because this is an equation where if you're going to do something to one side, you're going to do the same thing to the other side. Nothing has changed in algebra where you're not just doing the derivative to the right side and saying that the derivative equals x, 2x. That's what you've learned in the power rule. Let's pretend you don't know that right now. So I'm teaching you the power rule right now. So that's really y to the first power equals x to the second power. Like that's an equation. And we're going to do the power rule to this. Remember, it's just like everything you've learned in algebra. If we're going to do something to one side of an equation, we have to be fair and do it to everything. So to do the derivative here, using the power rule, it's the same power rule. That hasn't changed. So you take the exponent, you stick it up front here, and then you subtract 1. So this is going to be 1y to the 0 power, and this will be 2x to the first power. However, when we do derivatives to variables, you have to state it. You actually have to put something there stating that we have a derivative going on. So that's really what this is going to look like now. So here's our power situation. And now listen to how I say this. We did the derivative of a y variable, dy, and we're doing things with respect to x, dx. Doing things with respect to x because x is independent. Same thing here. We're taking the derivative of an x variable, derivative of an x, and we're doing it with respect to x. So we're stating that we've taken a derivative on both sides. We have to be fair, do it to everything. So let's clean this up a little bit. Y to the 0 power is just 1. And dx over dx, I know this is kind of strange to see it like that. And later you'll talk differential equations and you'll treat that symbol kind of like a fraction anyway. So think of it as a fraction for a second, and it's really just 1. It's dx over dx. So this is 1 times 1 times the derivative of y with respect to x equals 2x times 1. So now what you've been doing all this time in chapter 3 is you see something like this, and then you'll say y prime equals 2x. Well, that's the exact same thing as this. And those steps that are above it, these steps here actually happened invisibly, I guess you can say, or, that's the background of things that's going on. Okay, let's do another one. Same thing, but it's a little uglier this time. So y squared equals x cubed plus 4x squared minus x plus 1. So every time you take the derivative of a variable, any term, everything, you have to state that you're taking the derivative. So for the power rule, again, this will be 2y to the first power now. Oh, I'm sorry, I forgot that I threw that in here. The x to the 0 power, that's in here. If it doesn't have a variable, it's actually invisible. There's lots of invisible things in math. So x to the 0 power is just 1, so we treat that like an x to the 0 power if it's a constant. Anyway, when we do the derivative here, we're going to take the derivative of every term, state that we've done the derivative to every term. So this one is going to be 2y to the first power, derivative of a y, doing it with respect to x. This one's 3x squared. We just took the derivative of an x variable, doing things with respect to x because it's the independent variable. This one's going to be 8x to the first power, just did the derivative of an x, did it with respect to x. This will be 1x to the 0 power, another derivative of an x, and we're doing things with respect to x. And now this one, I mean, technically I should put the dx over here too, but it just equals 0 because 0 times 1 is 0. Remember, the derivative of a constant is always 0. It's because when you graph a constant, it's a horizontal line, and the slope of a tangent line of a horizontal line is 0. Okay. Again, every time you take the derivative of a variable, you're just stating the derivative of the variable you're taking and the derivative that you're taking, or the variable that you're doing things with respect to, which anytime you're dealing with x and y, it's always x. All right, clean it up again. This is a 2y dy dx. This one doesn't change. We don't really need this 1 right here, so we just put 8x. This is a 1. We don't need that. And the 0, we don't need that. You know what else we don't really need are these either, because it's assumed that they all equal 1. So you don't really have to write it because it's assumed that when you take the derivative of the independent variable, that you're going to be multiplying it by a 1 there. Like, it's assumed that that's happening and you don't really have to write it. So if you're my student in the classroom, and I taught you this, I would actually teach you this as I'm teaching you the power rule. Like, you wouldn't have done any derivatives yet, and I'm showing you the power rule the first day, and this is how I teach it to you. So you can just kind of get used to seeing that crazy notation because it's always there. And then when you get into the applications chapter, which is chapter 4, especially section 405 here, it's called related rates, you're going to be using these notations a lot more. So you just have to take note of every time you take the derivative of a variable, that you take note of the variable that you're taking the derivative of and which variable is the independent, which again, x in this case is always independent when you're dealing with x's and y's. Or time, when you start talking about time, things moving with respect to time. Okay, hopefully that wasn't horribly confusing. Let's do an example. That's a really nasty one too. Gotta love it. Find the slope of the graph of the square root of 2x plus the square root of 2y plus 2xy at the point 2, 8. Awesome, because we're going to take derivatives of all this stuff, and there's layers. Chain rule still applies. All right, so let's go. So first of all, it's always helpful to write the radicals as powers, just because those are exponents. So chain rule is going to be this comes out. We're going to subtract 1. We leave this alone, and then we multiply by the inside, the derivative of the inside. Same thing. Put this out front, subtract 1, leave the inside layer alone, and then you multiply by the derivative of the inside layer. And then remember, when you take the derivative of these x's and y's, we're going to have that dx, dx, dy, dy. We're not going to write, I'm sorry, dy, dx. I said that wrong. We're not going to write the dx, dx, though. We don't need that. It's assumed when you take the derivative of the independent variable that you don't need to write that. This side, take note that x and y are being multiplied, and you're going to need the product rule. All right, so derivative looks like this. Woo! Okay, so power rule, And then we leave the inside alone, subtract 1. 1/2 minus 1 is negative 1/2. And then you multiply by the derivative of 2x, which is times 2. So here's one piece right here. This is the x piece. Next piece is the 2y to the 1/2 power. So again, power rule, the 1/2 in the front, leave the inside alone, and then subtract 1. And then you multiply by the derivative of the inside, which in this case, when you take the derivative of a y, doing things with respect to x, you take the derivative like normal, which the derivative of 2 times a variable is just 2, and then the variable has, like, you're going to use the power rule here. That's y to the first power inside there. So 1 times 2, and then you end up with y to the 0 power. But then we just took the derivative of a y with respect to x. So be careful with that. Okay, so then the right side is we're going to treat 2x as the first piece and then the y as the second piece. So when I do the product rule, I've always just learned to say it to myself. It's the first times the derivative of the second. So that's this piece here. And if the derivative of y to the first power is just going to be 1 and then dy dx, so the first times the derivative of the second plus the second times the derivative of the first. So very messy, but this is the derivative of that expression. Okay, I just wanted to clean that up a bit. So the brackets here represent the derivative of the first part, brackets here represent the derivative of the second part, and then each of these sets of parentheses represents the product rule, each piece of the product rule. Okay, let's clean this up. This is really the square root of 2x in the denominator. And then notice that this 1/2 and this 2 cancel each other out. Everything's being multiplied right there. So the 2 and the 1/2 are gone. Same thing happens here. It's the exact same thing, except we have that dy dx going on. So now this is one term together. And on the right side, 2x dy dx is one term, and then 2y is another term. So this equation has 4 pieces, and we need to get dy dx by itself. So this is just like basic algebra. I know it's really ugly, but you just have to rearrange things. Put the dy dx pieces on one side, and you're going to use, like addition and subtraction because everything's being added and subtracted here. So if I want to move the dy dx's to this side, then I would subtract this piece. Actually, I want to include that plus sign with this because it's positive. Everything's positive, so I would just have to subtract stuff to move it to the other side of the equation. But instead, I put the dy dx's on the left here. So I took this 2x dy dx and I moved it by subtracting. And then I took this 1 over 2x, square root of 2x, and I moved it over by subtracting as well. So I just rearranged. There's 4 pieces, and I wanted to get the dy dx terms on the same side. Because the next step is if you have this situation, there's 2 terms here, 2 things. They're separated by this minus sign right here. You can factor out a common term, which in this case is the dy dx. So you move all the pieces that have the dy dx to the same side. You move everything else to the other side, just like a basic algebra problem. And then you factor out the common dy dx that they all have. And now you can divide because of this multiplication right here. Okay, now at this point, now that you have dy dx by itself, you can plug in the point. You have the x coordinate and you have the y coordinate. You just literally plug in exactly as is. I'm going to go kind of fast here. I'm running out of time. So you plug in the point, x and y, into all your x's and y's, and then you just simplify. You could probably just use a calculator, but I'm a fraction freak.